Now, you might be wondering about this electric field concept and whether this is just kind of a calculational convenience, and it is a calculational convenience, right? Because once you know the electric field at some location, you can figure out the force on any charged particle you want to put there without doing all that math again. Or is it real? And so I'd like to tell you about an experiment. We'll do an experiment together that's just a thought experiment, but it's a real effect. And here's what we're going to do. Let's see. What's your name? Travis, that's right, except you were sitting over there last time. Okay, Travis, I want you to hold up a positive charge in your hand here, okay? Travis is holding up a positive charge, and I take my little proton on a spring out, and I hold it here, and it stretches that way, right? So I'm measuring electric field in this direction due to the positive charge Travis is holding. Now, about how far away is he from me? About 3 meters, maybe? Something like that? We'll say he's 10 feet away, okay? Okay, now I want you to move the charge sideways. Okay, he moved the charge. You move it fast. Okay, so he moved it fast. Okay, 1 nanosecond, 2 nanoseconds, 3 nanoseconds, 4 nanoseconds, 5, 6, 7, 8, 9, 10 nanoseconds. Oh! Now I detect a change in the field. But for 10 nanoseconds, I was still measuring the original electric field. Thank you. You can put the charge down now. I was still measuring the electric field due to the original position of the charge. And he moved the charge, and it was only 10 nanoseconds later that my protons started going in a different direction. So apparently for 10 nanoseconds, there was an electric field here that wasn't pointing away from that charge. Now, approximately how long would it take light to travel from him to me? About 10 nanoseconds, right? So something seems to be happening at the speed of light here. Now, another possibility is even more interesting. What's your name? Kevin. Okay, Kevin, I want you to hold an electron in one hand and a positron in the other hand. Okay? So Kevin's holding up an electron, a positron. That's a dipole, right? Which one's the positron? That one. That's the positron. So I think I'm measuring an electric field like that, right? Now I want you just to let them go. What's going to happen when you let them go? They're going to be attracted to each other, right? And they're actually going to annihilate each other. And what's going to be left is 2 gamma rays, 2 high energy photons. Okay, so when I say go, I want you to let them go. Okay, ready? Go. Bam, they're gone. 1 nanosecond, 2 nanoseconds, 3 nanoseconds. We're not so far away, so maybe 7 nanoseconds. Oh, there's no electric field. But for 7 nanoseconds, I measured an electric field due to particles that no longer existed. So something was here affecting my proton even after those sources were gone. And this is fairly deep, and we'll see a lot more of this as the semester goes on, but it does suggest that maybe there's something real here. And maybe it might have some life of its own. Josh? Yes, it's definitely related to this idea that information travels at the speed of light. So his question is, if a star explodes and becomes a supernova, and then it goes out, and suppose it's 7 light years away, well, we continue to see light from that star for 7 years, and then suddenly it's not there anymore. But we saw it 7 years after the star exploded because it took the final photons 7 years to get to us. And so the speed of light and the speed at which electric fields and information about electric fields can change are indeed intimately related. And by the end of the semester, we'll see how intimately related they are. But there are some interesting relativistic properties of this here.